Oh, I can start. So you can record if you want. Can I? Are you recording?
Yeah.
Okay. So welcome again, everyone, and thank you very much for the introduction, Vedat. As Vedat said, today we'll be talking about linear regression. Why? You might think that there are other cool algorithms, right? Newer ones, novel ones. And linear regression is almost 200 years old. Why start with linear regression? Mainly because so linear regression is relatively simple. It's a simple algorithm, but we can understand many fundamental concepts regarding machine learning using linear regression. So that's why I wanted to start with linear regression. And hopefully at the end of this session, you can use linear regression on your own and on your own data. Also, you'll understand what is going on under the hood, right? So let's start. Instead of telling you what linear regression is and like explaining it using a PowerPoint, I want to show it actually. I want to show you what it is, and I think that's a better way to understand, start understanding what linear regression is. So here the idea is for you to just to get exposed, right? I won't explain all the details. I'll just want you to be exposed to linear regression or machine learning in general. Throughout this session, we'll use a library called scikit-learn. This is a very popular machine learning library that can run on Python. And it already has quite a bit of data sets preloaded. So what I can do is I can just load one data set. In this case, it's the diabetes data set. Here it's the first 5 entries. This is called a data matrix. This is very common in machine learning. So it's important for you to understand what this is. These are patients, 0, patient 1, patient 2. So these are called examples, data points, instances. It has different names. And these are the futures. So for one patient, age, sex, body mass index, blood pressure, and 6 blood measurements. These are called futures or attributes. Again, many different names. And this, for this problem, this is our target. We would like to predict disease progression 1 year after a baseline by using these futures. Another name in statistics, we call this the dependent variable. These are the independent variables. Okay. To keep this, to start simple, instead of using all the futures, I'd like to use only one future. Only this one, the body mass index. Let me plot this. Okay, so actually, let me do this. You can see this is the data set we have for the independent variable and the dependent variable. So for this problem, we would like to predict disease progression only from body mass index. In machine learning, the other fundamental concept is training set and data set. So instead of fitting a line to the data, what we do is we divide the data set. This 300 is arbitrarily chosen. And what we do is, instead of using all, we use part of the data set, the blue ones, to train the algorithm. And we would like to check the performance of the algorithm using the orange data set, right? In scikit-learn, this is actually very simple. You just need to call the objects, the linear regression objects, and this is the learning stage. This is where learning happens. You just say, this model you called, you can change the name of it, dot fit. And here you say, these are my independent variables. These are the dependent ones. We show them by X and Y. And we say just fit. That's it. Okay, this is very simple, right? With just one cell, we can fit a line to our training data. Now, with another cell, I can just get the predictions for the test set. This is how you do it, dot predict on the test set, right? Okay, now how can I check the performance? I have the predictions. I want to check the performance. What I can do is simply just like print the first 10 data points, 10 predictions, and 10 labels. So in machine learning, again, we call these labels the ground truths. These are the real values that we are trying to predict, and these are our predictions. And we can see that it's not very good, right? There's quite a bit of difference, but still it is learning a trend. Actually, just from the start, by looking at this, you can say that, okay, there is a trend here, but we cannot learn a lot just by fitting a line. Because if I fit a line, my prediction for this body mass index will be here, right? But the values vary a lot. But still, this is a nice example to start with. Okay, so these are the first 10. Let's quantify this. We can just take the difference, right? We can just take the difference and see how much error we have. And maybe you're interested in the average error, so we can take the average. But if we take the average directly, these will cancel. So instead, we can just take the absolute value, right? We can turn all the errors to positive values and then take the error. And this is called the mean absolute error, right? Mean absolute, this is the error. But just for the 10 data points, we want to do it for all test data. They are very close. And this is called the mean absolute error. And as you can guess, this is already implemented in scikit-learn. You can just call that metric and check that should be equal, right? Actually, it is a nice way to understand what is going on. What is this metric? If you implement it yourself, you'll understand, right? So when you first use a metric, try to implement it yourself and check if you get the same result. Then you can use this one, of course, because it might be a better implementation, right? But this helps you understand what is going on under the hood. Okay, so now we can actually plot our fit. So this is the line we learned from the blue data points. And as you can see that it's not a, so the error would be this, right? For this data point, this is the error. For this data point, this is the error. So it's quite high. Okay, so this is an example of linear regression. I just wanted to show you how it looks like, right? Not all the details. You can discuss if you have questions, of course, but just for you to give a general picture. As such, I want to give you a deep learning example from the start. This time I'll use Keras. This is another machine learning library. Specifically, it's a deep learning library, so you can develop neural networks with this library. Again, there is a predefined data set here. It's called the MNIST. These are handwritten digits with 28 by 28 images and the labels. So I can randomly show you some images. This is 7. This is 7 again. 5. So we have 60,000 training images and 10,000 test images here. So let me just run this because training takes a bit of time. So, okay, now it's actually training. you are seeing that the neural network is training. Let me explain what I did here. So this part is just creating the neural network. The neural network has 72,000 parameters. I'll explain what parameters are, but basically the aim is to learn these parameters. We are looking for these parameters. Then I defined an optimizer. In this case, it's stochastic gradient descent. Defined the loss function, and I wanted to check the metric accuracy as my performance metric. I had to do some shape changes for this to work. I want to point out that in the linear regression case, what we are learning, this line, is actually we are learning two parameters, right? A line is defined by its intercept and its slope. So these are two parameters we are searching for. If we know these two values, we know the line. In this case, we are looking for 72,000 parameters. So essentially, they're the same, right? In the first one, the only difference is actually the size. In the first one, we are looking for two parameters. In this one, we are looking for 72,000 parameters. Of course, there are other differences, but fundamentally, they are the same. Okay, training is done, and we already have 98% accuracy on the test set. We can actually check this by on one test image. I can randomly get a test image and say, this is where prediction happens. I say on model 2, predict the random image and get the prediction. As you can see, let's see if we'll get an error. 7 is correct. Well, it's working pretty nicely. But if you repeat this enough, you'll see some errors, and you observe that actually we humans might make similar errors. It's not, there are some images in the data set that are not really easy to recognize. Okay, so your first challenge right away is to load the diabetes data sets and repeat the first example. Just fit a line only with this feature, body mass index. Then, on top of that, there are some additional challenges, additional sub-challenges I want you to do. So instead of using the mean absolute error, use other metrics, right? For example, another popular one is mean squared error. You can see all of them here, all the metrics, but this is just one example. Just pick whatever you want and compare. And check which one is better. Try to think why, and try to think in which kind of problem you would prefer one metric over the other. Because choosing a metric is very important, right? There is no one metric that is good for all problems. You need to choose a suitable metric for your problem. So it's a nice exercise to do. And then, as I explained, there are two parameters we are learning. So I want you to use scikit-learn to print the intercept and the slope of the learned line. It's very simple. If you check the documentation, you'll see how to do it. Then, as we discussed, we only used body mass index, but it was not really, its predictive power was not as high. So maybe add more features, right? Instead of just one feature, create the X with more features and fit again and see if the performance improves. It should improve, but check this. And if you want, you can also check other algorithms. It's very simple because you don't need to do this challenge. You don't need to understand what is going on. What you need to do is just to call another algorithm instead of linear regression. Call random forest, and the rest is the same. Just model 3 fit X and Y, right? This is just to see and compare algorithms. Okay, so this will be your first challenge. Let's move on to the presentation. let me know if you have any questions at this point, please. If not, I'll move on. Okay, so I already explained the first challenge. It's to do linear regression using scikit-learn, the popular machine learning library. I'll present you in the following slides and code. I'll present you with additional challenges. The idea with these challenges is to push you out of your comfort zone, right? I want you to struggle because that is the only way to learn. But I checked your backgrounds, and we have quite a mixed group here. Some, like, it's 50-50 that some of you have some machine learning experience and others none. Some of you took no course, and one of you said, I took all of them. I don't know what that means, but so there's quite a bit of difference within the group, right? Also, in terms of your level of statistics experience and software experience, we have both low and high. So what I would like to propose to you, so your comfort levels are different. So what I want to propose is, do not try to solve everything in 3 hours. Instead, just if you find a challenge very interesting, you can spend 3 hours or more on just one challenge, even one sub-challenge, right? And if you find, for example, this one very easy, you can go to challenge 4 or whatever, right? So this is more or less the structure. I will explain you these challenges for 45 minutes roughly, and then the remaining time you will try to solve the challenges. But please don't think that you have to finish everything in 3 hours. It's just the idea is for you to explore, right? Okay. A little bit about myself. My name is Alican. My background is actually in material science. It has nothing to do with machine learning or software engineering. After my PhD, I started getting interested in machine learning and teaching myself machine learning. And I actually started applying machine learning to my previous projects related to photonics. And seeing that I can create some value, I decided to start a company called Ipsimio here in Eindhoven. It's been just more than a year ago. What we do at Ipsimio is applied machine learning. In this case, so these are two examples. This one is from physics, and this one from healthcare. We can talk about this later if you're interested. Okay, so I think we are set. We are ready to go. First, I wanted to show you, right? Show you what machine learning is, but we also need to define what machine learning is, what AI is. So now I would like to define these terms. So let's start with AI, actually. What is AI? Unfortunately, AI is not it doesn't have an objective definition. It can change depending on me and you, because, so consider a man-made object. If you think that it exhibits intelligent behavior, according to you, then it's AI. To me, maybe it's not AI. Or maybe 20 years ago, you think that something was AI, and now you think, oh, that's trivial, right? It's not AI. So this is a bit problematic. It doesn't have a very objective definition. But the ways to achieve AI, like machine learning, symbolic AI, they have concrete definitions. So let's move on to that. It's better to use machine learning as a terminology instead of AI. So what is machine learning? Machine learning is simply learning from the data. In the 1980s, they were trying to do symbolic AI. Symbolic AI is you are trying to write the rules by yourself, not learning from the data, but human experts were putting their expertise into code. So these were called expert systems. They thought in 1980s this was the way to go, but now we know that it's not the case. So in case of machine learning, we are not explicitly writing the rules. Instead, we are providing the data, like the handwritten digits, and let the machine learn the relationships. Okay? And within machine learning, there are different ways to do this. One fundamental categorization is supervised versus unsupervised, but there is a territory in between. For example, reinforcement learning is in between supervised and unsupervised. And within supervised, we have different algorithms. For example, linear regression, for example, random forest, neural network. We'll see these algorithms as well in different the next sessions, right? Supervised machine learning is when we provide the labels, right? We provide the image of a digit and we tell the computer the label of it. We say, okay, this is 0, this is 1, this is 2, right? So this is called supervised machine learning. And neural network, the way it works is fundamentally different than the others. So they came up with a different name for it, which is called deep learning. The main difference is this learns layer by layer. Instead of learning at one go, it learns first simple, let's say simple relationships, and it gets more complex. That's why it's called deep learning. One other categorization I would like to talk about is regression versus classification. So in the examples we saw both regression and classification. The diabetes example, it was regression because we are trying to predict a continuous number, right? So it's called regression. And in classification, we have categories. In digits, it was 10 digits, right? The output could be any of those 10 classes, but nothing else. So that is called classification. So now we'll move on to the fundamental equation of machine learning. But before doing that, I want to just mention one more thing. That is, what can you do with machine learning? There are, let's say, two main directions you can follow. One is machine learning research. The other one is applied machine learning. The aim with machine learning research, the idea is to come up with new algorithms, new machine learning algorithms, or let's say new ways to train algorithms, like better ways to train them with faster optimization algorithms, or let's say being able to make them work with less resources, etc. So this is called machine learning research. Applied machine learning is you take the developed algorithms here and apply to a problem in another domain, like healthcare, like physics. So here, actually, for applied machine learning, it doesn't matter much which algorithm you use. The key here is, can you create value in a domain, in physics, in healthcare? Can you create value? I don't care how you create that value if you use a convolutional neural network or a very simple one, a simple random forest. I just want to see value in the domain. So they are pretty much different from each other. Some people or some companies, you'll see that they do both, but mostly you have to choose one or the other. Okay, now we can move on to the fundamental equation of machine learning, which is data is signal plus noise. Again, the best way to explain this is using code. So let's go back to Jupyter. So what is data is signal plus noise? So normally in real life, we have data, but we don't know the signal, we don't know the noise. We are looking for signal. The idea in machine learning is to find the signal inside the data. To be able to understand this, what I'll do is I want to generate data, because normally we have data, but we don't know what the signal is. And in that case, it's hard to understand what is going on. But if I generate data, the way to generate data is first to generate the signal, then generate a noise, and then combine them and generate the data. So if I do this, I have the data, but I know what the signal is and I know what the noise is. So it's really useful to do this to understand what is going on here. Okay. So for this example, I'll use Newton's second law as my signal. So what this law says is, if there is a mass with 2 kilos, and if we pull this with 10 newtons, the acceleration will be 5 meters per second square. This will be the signal in this part. We can view this equation as a line like this, right? The intercept plus slope multiplied by f. Here, the slope will be 1 over m, intercept is 0. This is our signal. In this case, it's just 1m and 1f. But what I can do to generate data, I want to generate multiple data points, right? I can say, okay, I want random f's between 0 and 1, 10 random f's. To change the range, I can just multiply it by 100. Now I have force values between 0 and 100. I can calculate the acceleration, and I can plot them. Okay, where is it? Here. This is the data I generated, but this is only the signal. I can add noise to this. Here, it's the same code, but I just generate some random noise here and add it to the signal. And now we have the data. Again, the good thing here is I have the data and I know the signal. I know the signal. I know how I generated this. So I can actually plot the signal and data together. So this is the signal I use to generate the data, and this is the data, right? I generate first the signal and then add some noise to it to generate the data. And you can consider this as like this for this example, right? Data is signal plus noise. Instead of plotting just the points, I can plot the signal as a line and show the noise like this. So this completes this equation, right? Data is signal plus noise. The meaning of this is this. I have this signal, I add noise to it and generate data points. In real life, we only have these data points, and with machine learning, our aim is to find this line. We don't know this line. We don't know what is noise. We are looking for this line. This is what machine learning is. So actually, let's see this, right? Let's fit a line to these data points. Again, I just call this object and then just say fit. And I can plot my fit. As you can see, this is the fit. And it is close to the signal. Not exactly, but still it's very close. If I increase the number of data points, you will see that it will be almost exactly the same. Actually, it's a nice exercise to try if you want. Increase the number of data points, and you'll see that this will get closer. So one important, now that you know what fit is, what signal is, and what noise is, one important thing to understand here is the different types of uncertainty. So imagine I have this blue, this is a different, just one data point I generated, nothing to do with this one. Imagine this is my fit, the blue, and this is the signal, and this is the data point. So if I have this input, this will be my prediction, right? The fit means, okay, I put this value and I get out this value as my prediction. And this is its actual value, the label. So the difference between this and my prediction will be my error. And error has two components. Error is caused by two different things. So you should think about error not as a single entity, but it has two parts. This is important. One is caused by the difference, how good your fit is, right? You are trying to get as close to this signal as much as possible. And this difference will be your epistemic uncertainty. In principle, you can learn more. With more data, you can decrease this. And that's why it's called epistemic uncertainty. And then there is this noise. You cannot learn this noise. That's why it's called aleatoric uncertainty. It's kind of like random uncertainty. For a fixed data generation process, you cannot decrease this. But let's say you use a new method to collect data with better resolution. Then this noise will also decrease, right? So the other name, there are other names for these. Actually, it's called reducible error and irreducible error. But I didn't want to use it because you can actually reduce this one as well. Even though it's called irreducible error, you can, in practice, reduce this by collecting the data better, right? For a fixed data set, you cannot change this. But in practice, you can change your data collection and improve this. Or you can add one more feature, for example. Instead of using just body mass index, if I add more features, this error will also go down, okay? So now your second challenge. What I want you to do is to plot these uncertainties with respect to the number of data. So instead of 10, increase the number from 0 to, I don't know, 100 to 1,000, and plot these two and see what happens. And do the same this time with respect to the noise. Change the noise level for a fixed number of data. Change the noise level and see what happens. Here, you might need to find a suitable range, right? So fix the number of data. If you fix it to a very high data point, let's say 1,000, 10,000, then you might not see what I want you to see. So you need to search for a good number here so that you get a nice curve. And before plotting, please try to guess what you'll get when you plot these two, okay? Understanding this uncertainty data is signal plus noise helps us understand overfitting. Overfitting, probably you all heard, this is the fundamental issue, fundamental problem of machine learning. If you're overfitting, your model will look like it's working fine, but in practice, it will perform poorly. That's why it's important, very important, to understand what overfitting is and to understand the ways to prevent it. Okay, so let's see what it is. Let's go back to our previous example, not this one, but this one. Plot it again. And let's fit a degree 5 polynomial to it. Simply, I can do this with NumPy and plot this fit as well. Okay. So let's see what's going on here. As you can see, it seems like the red one follows the data points better than the blue one, right? It is closer to the data points. So if we measure our error on this training data will be lower with degree 5 compared to degree 1, right? So is this better? Is this a better fit? Because if I measure my error, it's lower. No. How can I understand this? What I can do is I can generate new data. Since I have the signal, I can generate as much as data I want. I want to generate new data and test the models on this new data. So I generated new 10 data points. And what happens here is, as you can see, suddenly this red curve that followed the training set very well is not following the orange that well, right? So what happened when we went from the training data to testing data? The performance of degree 1 stays the same, almost the same, right? But degree 5 goes from very well to very bad suddenly. So this is called overfitting. So when you change something, when you do an action, right? Let's say in this case, the action is instead of degree 5, instead of degree 1, I fit degree 5. What will happen here is your training performance will increase, your testing performance will decrease. This is what overfitting is. You might hear that some people refer to overfitting as, okay, my test error is lower than training error, this is overfitting. That's not a good definition of overfitting. You need to define overfitting with respect to an action, right? I increase the degree I fit, and what happens in response is my training error decreases, my training performance goes up, but my testing performance goes down. So this is what overfitting actually is. And of course, your third challenge. So what I want you to do is to calculate the training error and test error for both of these fits, right? So calculate the error with this data for these fits and with this one for these fits again. And what I want you to do is to fit, instead of just 1 and 5, just say, okay, degree 1 to up to, let's say, 10, 15, fit different degrees and plot these errors you calculated here and see what will happen. And finally, what I want you to do is, here we have the data generation process we had was degree 1 already, right? So I want you to generate data with a higher degree. I said, okay, quartic, degree 4, but it could be anything. It could be cubic, degree 5, whatever. But just then generate data with even x square, cubic, whatever. And do the same here. This will help you understand what underfitting is. I'm not going to explain what underfitting is to you, but hopefully when you see the plot, you'll understand what underfitting is. If not, we can always discuss what this is. This is also very important, so you need to know what underfitting is. But I leave it to you. Okay? Okay, so this completes the fundamental, what this data is, signal plus noise. And we can move to our challenge 4, right? So we saw these 3, and now we move to the final challenge. So simply here, in one cell, you did a fit, right? You just, using scikit-learn, you were able to fit a line to the data points. In challenge 4, you'll implement it. Instead of using scikit-learn, you'll just use Python and NumPy to do the fit yourself. Okay. One point here: there are many ways to solve this problem. Okay, this is just one implementation using gradient descent. Maybe with scikit-learn it's a different implementation. Actually, I think they use singular value decomposition. I guess I need to check, but it doesn't matter. I want you to learn gradient descent specifically because even though we can solve linear regression with many different ways, when you go to neural networks, the only solution that works is gradient descent. That's why I want you to learn gradient descent. Okay, so let's see what gradient descent, how you can fit a line using gradient descent. For this, I'll have a running example, house price prediction. Simply, the idea is to predict from the size of the, this is very similar to the body mass index diabetes problem. From house size, you have to predict the price. Imagine you have collected a data set of 27 houses, okay? In this case, I'll refer to this number as m. Unfortunately, you might see different uh, different symbols for the same thing. There is no really one consensus on how to. So you will see, for example, n here. N as the number of data points. Some people use m. But it doesn't matter. Just know that it could be different. You just need to understand what this refers to, right? We need the notation to make the equations. That's all. So in this case, for this session, it's m, the number of data points, and we would like to fit a line to it, right? The way we represent these numbers, the examples, the instances, are as follows: xi and yi. For example, if I want to represent this, it will be x2, y2. Okay? This is the independent variable. This is the dependent variable. And for this example, I'm using only one future. Future is represented with n, and it's 1. Okay, so our aim is to fit this so that when we have a new house, right? So we don't care about training data. We care, once we learn it, we care if I give you a new house, can you predict the price? And this is the equation of the line. I can just put this value here and get the prediction. And as we discussed, we are looking for these two values, right? These two parameters. These are called model parameters. This is called a weight. This is called the bias. That's maybe you heard weights and biases. These are model parameters. Okay, so how to find the line? Which line? I mean, is this line better or this one? Right? This line passes through more data points. Is this better than this one? Remember, again, our aim is not to pass through data points. Our aim is to find the signal, right? That's why this is not a good fit. We can see already that the trend looks like this. So this seems like a better fit. But how do we quantify this? We don't know the signal. So for now, we have to use our training data to quantify our fit. So what we'll do is, for this example, what is the error, right? Error is the difference between prediction and the label. This is our data point from the data set. This is our prediction. And the difference is error. In machine learning, we represent the prediction with hat. Y hat means the prediction. So this is the error for just one data point, right? But as we discussed, we are interested in the error of all data points. So I can simply sum the errors, right? But the point here is if I sum, the negative and positive errors will cancel. So I can take the square of it. In the previous example, I did the absolute value. I can also take the square to solve this problem. And one more thing, I'm interested in the average error. If I just do this, my error will change depending on how much data I have, right? The more data I get, my error will increase. So I don't want that, so I want to take the average. Finally, I put this 2. It's not necessary, you don't have to put it, but when I take the derivative, as you'll see, these 2 will cancel. That's the reason, but you don't need to put this. So this equation, and once we replace the prediction with this, right? The way we get the prediction is by putting x to this equation. So I replace it, and this is the final equation we are interested in. This quantifies our error with the fit. This is called cost function or objective function. There are many names again, but we'll use cost function. If we can find the parameters that minimizes this equation, we'll find the line. We'll find the best line, right? And this is our aim. We would like to minimize this function. How are we going to minimize this function, cost function? Let me just show you an intuition using a very simple example. Imagine we have this, say, 5 data points, and we start with a random line. In this case, I wanted to simplify this by fixing the intercept to 0. So theta 0 is 0. And I randomly pick a line, and I can calculate the cost and plot, right? For this line, this is the cost. Okay, this is the equation, right? This is 0, and I calculate this and get this. So for this line, this is the cost. For this line, this is the cost. I do this for different lines, and actually you can see the trend here, right? So this is how this equation looks like when I change the parameter theta 1 and keep the theta 0 fixed. So our aim is to randomly start at some point, could be here, wherever, and reach here. We want to find this. What if, now you might ask, right? This is a simplified version. What if I have a line like this, right? Not fixed theta 0, but some other value. In that case, this will look like this, right? So this is as if adding another axis here. So this is theta 1 axis, and I'll add theta 2 axis here. So it will be a surface like this, right? I'd like to mention one detail here. It's that the shape of the surface is important. So this is why in machine learning, it's important to normalize your input data. We want the scale of your features to be similar so that the loss surface looks like a circular one. Instead of an elliptic one, an elongated surface, we want a roughly symmetric one so that the descent, gradient descent, we'll explain, is more smooth. That is why we normalize our input data. We can discuss this later again. In this session, you don't need to normalize the data. It will already be normalized. But if you want to test algorithms on your data, be careful about this point. Not all algorithms require normalization. For example, if you want to fit random forest, you don't need to normalize. But still, keep this in mind. Okay, so let's move on with the simple example again and see how gradient descent works. So I explained to you the cost line, right? But in reality, we only have the first point. We don't see this curve if we don't plot it. So how do we know to go to this point? How do we know that the minima is here? In this case, what we can do is calculate the derivative of this function. If we calculate the derivative, we know that derivative shows us, okay, the slope is positive. That means if I move into this direction, the cost will increase. And if I move into this direction, the cost will decrease. So I know that I want to move in this direction. The derivative, I calculate and decide which move, depending on the sign, I can decide where to move, right? So let's imagine an arbitrary step, 0.5. I start from 2.5, see that the slope is negative, so positive, so I want to move in this direction, negative. Arbitrarily, I go to 2. So I update my parameters. I started with a random theta, and now after one step, my theta is 2, closer to the value I'm looking for. Then I go to this point, calculate the derivative again, still positive, so I need to move to left, right? So if I do this, if I repeat this, I'll reach this point where the slope is 0. So we can write a rule as such, right? Repeat this until slope is 0. This is like the initial form of gradient descent. But there are, of course, some problems with this. Why 0.5, right? This is an arbitrary step. We cannot find a suitable step for every problem. So what do we do? What we do is, instead of this number, we can say, okay, I'll put a learning rate and the derivative itself. So I'll just put the derivative. So this will give me the direction and actually also the amount, right? But I can control that step size with learning rate. This is an hyperparameter. So model parameters, this is a model parameter. These are things we learn from the data. But a hyperparameter is something we set before training. That's why it's called hyperparameter. Okay? And instead of this repeat until slope 0, maybe the slope is never 0. So we can say repeat until convergence. This is again not really explicit, right? What is convergence? We can define something as convergence, but I will discuss this point later. Okay. So this is how gradient descent looks like for just one parameter. You might say, is it the same if I start from the left? Yes, because this time the slope is negative, right? So I know that if I move in this direction, it will increase. If I move in this direction, it will decrease. So the formula stays the same. And now the important question is, what happens if I have more parameters, right? I will never have one parameter in practice. So in that case, we'll use partial derivatives. So for each of those parameters, the equation becomes like this. And this is called the gradient. For multivariable calculus, the derivative, let's see, I mean, this vector here, this is a vector, right? 1, 2, 3 components. This vector here is called the gradient, and that's why this is called gradient descent. We'll use partial derivatives with respect to this parameter to calculate this. And what we'll do is to repeat until convergence, whatever number of parameters you have. Okay, this is kind of like the general form of the equation. And let's calculate this for our cost function, right? We define the cost function. Let's see what this is. If I take the partial derivative of this function with respect to theta 0, what I'll get is this derivative of this, right? This 2 goes here, they cancel. And the derivative of this inside with respect to theta 0, which is 1, right? The coefficient of this is 1. These are like constants because they're not changing with respect to theta 0. If I do this for theta 1, I do the same, but this time the derivative of the inside is this, because this is the coefficient of theta 1, right? If I take the derivative of this thing, it's this. So I put it here. So this is what you have to do, actually, right? For you, I showed you the calculation, how you are going to do the gradient descent. You need to implement this function for implementing gradient descent. When you implement, please think about the fact that maybe you might have more features, right? So think about the general equation. This is one step of the gradient descent, right? And you need to repeat this until convergence. You start with random theta, you update it once, and you repeat, and then you repeat until convergence. I'll discuss what convergence is. One final note before we move on to the challenge. It is the dot product or the matrix multiplication. So if you want to, let's say you have x, you have this equation, and you have thetas, and you want to calculate y for each x. If you want to implement this in Python, please don't write a for loop. Instead, use matrix multiplication. because with matrix multiplication it's much more efficient, right? So to get this, I can just say this is x, this is theta, and I can just calculate y as follows in one line. Notice here that I've added ones here. Why? Because to be able to do matrix multiplication, what is gonna happen is I want to take the dot product of this row with this column. So this should match with some value, and that's 1 fixed, right? So consider as if there is, instead of just theta 0, here we have theta 0 multiplied by 1. This is what that 1 is. So we can simply calculate y in one line. Use this in your implementation. There is also in NumPy matmul, refers to matrix multiplication. I think that you can also use that one if you want. Here, please take care of your the shape. If you have a shape like this, you'll get an error. You have to take care of the shape. You can change the shape using NumPy reshape or even NumPy new axis. Okay. Okay, so this is the summary. These are the functions you have to implement. First, you need to implement this cost function. Given x, y, and a random theta, you need to be able to calculate the error, right? Using this equation. Then you'll implement gradient descent one step, one update, using these equations. And finally, this is pretty simple, because if you can implement this, this is just looping this, right? You just repeat these steps, and that is your gradient descent. Okay, let's move on to the code. I'll show you how it looks like. Okay, so let's see. To be able to do this, we'll again generate data. Okay, let me generate 10 examples with one future. I'll get my x like this. And as I explained, I have to add ones, right? I add ones as follows. I can start with a random, I mean, not start, but to generate the data, I need a theta, right? But I'll just pick it randomly. This is my theta, and I generate y, and I can plot x and y. Okay, so now with this data you'll generate, you need to fit a line to it. I just implemented this function so that you can plot the data with your fit. This, in case we know what theta true is. Once you find the theta, you can put it here and see how your fit looks like, right? And let's see how you will implement gradient descent. Okay, so what, as we discussed, you start with random weights. You don't know what theta true is. You just say, okay, randomly I'll pick a theta. And if you plot this random fit, you'll see this, right? Okay, this is your starting point, and you want to go to here. Sub-challenge 1, implement the cost function. So I implemented here hidden. You don't see how it looks like, but the behavior is as follows. It should be 0 if you put theta true, right? Because the predictions and y will be equal, so 0. And so for your random theta, this should be some positive number. It could be different than this number, right? Because we randomly generate the data. This is the first sub-challenge. The second one is to implement the first, like, one-step gradient descent, right? Given x, y, and theta, give me an output theta updated, right? So it will be like, instead of this line, a line that is a bit closer to this line. Not very much, it's just one step, but a little bit. So let me show you how it will look like. Okay, this is the random theta, and this is the true theta we want to reach to. So if I do this, let's see. Yes, I get a little bit closer, to, yes, I get a little bit closer, this theta to this theta true, with respect to this one, right? So this might not happen always because I just do one gradient descent step. But if you repeat this over and over, so if I repeat this like this, right? If I repeat, I have to see that this theta gets closer to theta true. And as I said, I mean, if I repeat this cell, repeating this is gradient descent itself. So your sub-challenge 3 is to write a function that repeats this update. Okay, so let's see how it works. I already did that, and you can see, let's see, yes, this is the, mind you, this is the fit. This is not the true theta, this is the theta that gradient descent function finds, and as you can see that it's pretty nice, right? One thing here, so to debug gradient descent, okay, this is the, I can also plot them together, the fit and signal, to compare. But I want to see how loss changes during gradient descent. So I want you to, additionally to sub-challenge 3, I want you to save the loss at each epoch, right? So what you'll have is, once you update the theta, just save the loss. And then you can plot it. Okay, you see? This is the behavior we want. We want that at every step to loss to decrease. And now I want to talk about convergence, right? So the shape of this curve is very important to understand if you are learning or not. Instead of defining convergence concretely, you can just look at the shape of this curve. As you can see, it looks like maybe I can learn a little bit more. Like it looks like, okay, it's going down, but not converged, right? It's not a flat line. So this is how you can define convergence. The flatter it gets, the better it is. Imagine you see something like increasing loss. That would mean you picked a learning rate that is too high. So I want you also to try actually different learning rates, right? Try different learning rates like 1, even 5, 10, and try to see this decreasing. If you pick something very low, like 0.0001, it will decrease, but it will decrease very, very slowly, right? So you need to find something just right so that it learns fast enough, but not too fast so that it overshoots from the minimum. So I want you to play, once you implement it, change this value and see how this curve changes. Okay, the rest is not, the challenge is, that's it, but the rest is the conditions your implementation should work. So we fit non-noisy data, right? This is like the ideal data, but your fit should work with noise as well. So what happens here, I just multiplied y with some noise and I generated noisy data. And now let me do a fit. Again, it looks like this is learning. You see that it works again. This time the fit is not as perfect. There is some difference, but still it learns with noisy data. And again, when you implement, please consider more features. So your implementation should work with more features. If I have 2 features, I'll again add 1. So this time I'll have 3 parameters. Add some noise. And it works again. So in this case, the last case is very close to reality, right? We have more features and we have noise. And it's still, the implementation still learns. And actually we can see, right? Just check the theta and theta true and see how much different they are. And also we can do a prediction. Yes, any
Alican, we
question? Yeah.
have 2 questions,
Yes.
actually.
Mm-hmm.
So one related to this code, which is where does the loss comes from? that you are explaining.
Mm-hmm. What do you mean by where it comes from? So let me go back to the presentation. Do you mean like where does this equation comes from, or like how do I implement it? What is the question?
I mean, when you plot the loss against the
Okay, so this plot.
epochs,
Yes.
yeah, this plots. Where does the lost info comes from? Like, where did you get that information? Yeah.
Okay, so let's do the following. So for each theta, right, you can calculate a cost. Imagine you start with the random theta. You say theta 0, theta 1, and you can calculate the cost. Your first dot here in this plot is that. This is your random theta's loss. Then with gradient descent, what you do is you update the theta, right? You update the theta and you move here. You calculate the cost again. It decreased a little bit. This is how I did this, right? You just, so let me go to here. So cost function, actually, I can show you like this. Where did I, okay. This is random weight initialization. Okay, I have to generate the data again. Yes, so let me generate this again. Until here, yes. So imagine this is the theta I start with, right? I have this cost function. I calculate this value. This is my first value. This is where I should go. Okay, so now I can put actually here this and see the cost. And now I do one step of gradient descent and I can now check the cost again. You see it decreased. Because I updated the theta using gradient descent, one step, and this is the idea, right? The idea is to slowly, I want to decrease the loss. If I repeat this step again, watch, if I repeat this again, this should decrease it even more, you see? So this is what gradient descent is, and this is what I'm plotting. At each step, this loss should decrease.
Thank
Clear?
you.
Yeah, sure.
Wait, I want I want to also ask about this loss function. Is the formula like fixed for this, or it just how you define the loss function to describe the error from the prediction and the true?
So there are infinitely many loss functions. In this case, this is the one that is suitable for this problem, for this algorithm, right? There are all kinds of fancy loss functions that we can come up with. But in this case, actually, this is why I explained it step by step here. Let me move on to, where was it? Here. So this is like intuitively a nice way to measure the error, right? But instead of this, I could have just said, okay, I want to measure the absolute value. One thing here you need to, I mean, this might be a little bit too much detail, but here differentiability is important, right? Because I take the partial derivatives. So I need to consider, I cannot just say any loss function, right? I need a loss function that behaves well when I take the differentiation. If this results in a very weird loss surface that is hard to go down, that would, I mean, I wouldn't want that. So it's a trade-off between your problem, right? The cost should be suitable to your problem, but it should also play well with the optimization. You might find the best cost function depending on your problem, but if you cannot differentiate, if you cannot easily calculate the partial derivatives, then you cannot learn. Then it will be a problem, right? So this is the balance you have to find. Is this clear, or you wanted to ask something else?
Is there any ways that we know like for which problem we use which function or?
Well, so for example, if the way to do it is as follows. If you have a problem that many people already solved, you can just check the literature and use that loss function. If you have a unique problem, then you need to think yourself, right? You need to think that, okay, what do I want to minimize? This is the question you need to ask to yourself. Okay, I have this problem. For example, one consideration you might have is, okay, I want in my application the error to be lower than a certain threshold. Once it's lower than that certain threshold, I don't care how much error I have, right? So what you need to focus is you then to minimize large errors, right? So instead of the average error, you say, I don't want large errors. I can tolerate small errors. Like for all 1,000 data points, I have small errors. I'm happy with that. But if I have one large error, that's really bad for my application, right? If this is the case, for example, mean square error is a nice one because it punishes the large errors more than small errors because you take the square of it, right? For example, this is how you might approach to selecting a loss function. I hope this answers the question.
Yes, thank you.
Sure. More questions? I'm about to finish already. I guess not.
How do you define the convergence?
Okay, so one thing you can do is if my loss is not decreasing, let's say you say 0.001, you repeat and you see that it's not decreasing more than 0.001, you say, okay, stop. But this is not a really nice way because depending on the problem, this threshold might change, right? So the best way is to not to define it, but to plot the loss surface, because that shows you if you're converging or not. Right? So the threshold, the value, the absolute values you read on the y-axis might be different, but it doesn't matter. What you want to achieve is a decreasing loss, and then that saturates at a level that you are happy with. So that's a better way. So instead of defining convergence, you define the number of steps. You say, let me go back to the code. Here, epoch, the number of steps. You say, okay, 1,000 steps, you check. Let's say, imagine you said 100, and you see that it stopped here, right? You'll see that, okay, this is not converging, so I need to increase the number. Actually, here we see that it's not really, maybe I can increase a bit more, right? And this is actually very important because depending on your problem, depending on your data set, the number of epochs will be very different, right? For some problems, actually even here, we saw that when I change the noise, etc., the shape changes significantly, right? So, and this is just the same problem, right? A toy data set. With real life, with very complex problems, these numbers will be different, but the shape will be the same. So this is why I want you to learn the shape, not these absolute numbers. So there is no specific number, I would say, to define the convergence or epochs. I cannot tell you that, okay, stop at 1,000. No. For one problem, you might stop at 200. For others, you might need to go to 3,000, 5,000, right? So better to learn what this looks like. That is why I want you to also plot this by changing the learning rate and see how it shouldn't look like. If you increase this to 10 or whatever, you'll see that it will be like increasing, or if you lower this, you'll see that it's decreasing but very slowly. So doing this will help you understand the convergence criteria. Okay.
Yes.
Cool. So actually, that's it, right? This is my last slide. So again, I want you to remember that I don't expect you to finish everything, right? I just want you to explore what you find interesting. Thank you very much. So I'll be here for the next 3 hours and try to help you with your questions. Let me stop sharing. Yes, so we can start with the challenges.
I think, Alican, you have also one question. Is it a problem if the loss function is non-monotonically